Alright, ladies and gentlemen, this is going to be the next video on photosynthesis. So let's get started on this next video. So if we're looking at this, we're going to be talking about the light-dependent reactions. So the reactions that depend upon light. And specifically, we're going to be looking at the electron transport chain. So what we're going to do on this side of the chloroplast is we are taking in water, we're running it to the thylakoids, and we're going to create oxygen. So we call these the light reactions, or the light-dependent reactions, because it requires light via the electron transport chain. So our goal here is to take ADP and generate ATP. And then we're also going to look at another carrier molecule here, NADP+, and we are trying to convert it into NADPH. So our entire goal here is to create energy in the thylakoid space to power the Calvin cycle. So we've been talking about NADPH a lot, but what is NADPH? Well, NADPH is an electron carrier molecule. It's similar to ATP. It kind of serves the same purpose, and it can carry high energy electrons and provide energy for chemical reactions. Now, when we're talking about NADP+, well, this is when NADPH has lost a hydrogen and electrons, and it's a carrier molecule when two electrons and this proton are missing. So here's the way I like to think about it. And this is going to be a really, really strange, weird analogy. I have this toy car, and this toy car is going to be powered by a hot potato. Now, here's the thing. I'm going to have to heat up that potato in an oven in order to get it hot. So we'll put the potato in the oven. Now, the potato is going to be too hot for me to touch with my hands. So I'm going to take that potato, I'm going to put it on an oven mitt. And then here's the thing about this potato. This potato is kind of weird. It doesn't like going anywhere without this purple toy ball. So I can't send the potato to the toy car without the toy ball. So I'll take the potato and the toy ball, and I'll bring it over to the toy car. And I'll put the potato into the toy car, and it will have its little purple toy with it, the potato will. And then this toy car will now have the energy, because of the hot potato, to go through and move. Now, I know that that was a really strange analogy, but here's where I'm trying to get at. This is going to kind of allow us to understand what NADPH is. So that analogy was kind of strange, but the way we're trying to think about it is, what are the parts of this NADPH compound and how does it go through and power our Calvin cycle? So if we think about this, the potato here, well, this is kind of like our high energy electrons. So high energy electrons. And its toy ball is kind of like that proton that we need here. So this is like that H+ proton that we need that's present for this specific reaction. Now, if we're thinking about the oven, well, the oven's kind of like the light, which is used to go through and heat up that potato and allow for the potato to go through and go down the electron transport chain. And then this toy car is kind of like our Calvin cycle. So this is kind of like our Calvin cycle. Now, the oven mitt is kind of like our NADP+ carrier molecule. So it's kind of like this up here. Now, when we go through and combine the oven mitt, the toy ball, and the potato together, well, the toy ball, the potato, and the oven mitt together are kind of like our NADPH molecule. So it's the combination of that proton, the two electrons, so the proton's kind of like the toy ball. Remember, that's our proton. Our two electrons, which are like the potato, and then the oven mitt, which is like our NADP+. So the entire combination of all of these put together is like our NADPH molecule, and we're going to use that to go through and power our toy car or power the Calvin cycle. So ATP and NADPH, well, these are energy carrying molecules that we use to release the chemical energy. We can do it via ATP, and we can also use electrons that are present to allow for that energy transfer to occur. And the main difference between ATP and NADPH, they're going to serve the same purpose, but ATP we're going to use hydrolysis to release energy, whereas we're going to oxidize NADPH to provide electrons. So if we're looking at the diagram here, my entire purpose of the light reactions is to power the Calvin cycle. So I want to power the Calvin cycle. Remember, the Calvin cycle, what I'm doing is I'm taking carbon dioxide, CO2, and I'm going through and turning it into glucose. So I'm turning it all into glucose, which is C6H12O6. So I'm taking carbon dioxide, and I'm converting it into glucose. Now here's the thing, this is going to require energy. The way that I'm getting that energy and where I'm getting that energy is from the sun. The sun is beaming down light on the thylakoids, and inside the electron transport chain, what I'm trying to do is produce NADPH, which has energy via electrons, and I'm trying to produce ATP. So I'm taking these two molecules, they both contain energy, and I'm going through and I'm sending them over here to the Calvin cycle. And then once I have the energy to power this Calvin cycle, now I can take that CO2 and glucose. The reason we call it light reactions is because over here we need light in order for this to occur. We need light for that NADPH and ATP production. Light independent reactions, well, we're just taking CO2 and glucose and we're using chemical energy to power that Calvin cycle. So we don't need light anymore on this side of the diagram. Okay, so this is where things get really, really complicated. So what we are looking at now is what we call the electron transport chain. Electron transport chain. And what I am doing here is I'm taking light-dependent reactions, and I'm converting it into chemical energy. So this is going to eventually produce ATP and NADPH. So my goal here is to create ATP and NADPH. So the first thing that's going to happen is beams of light are going to hit this first purple complex. So what we have here is just light. So this light's going to hit this purple complex, and we call this purple complex photosystem 2. So this complex here, this purple one, is what we call photosystem 2. And then this other square complex here, well, this is photosystem 1. So we'll say photosystem 1. Now the reason this one is not called photosystem 1 and this one is because this one was actually discovered first, before this one was discovered. So we call this one photosystem 2 and photosystem 1. Now if we're trying to picture where we are in the membrane of a thylakoid. So on this side of the membrane, so right here, this is our membrane. Over here we have the thylakoid space, and then on the other side here, this is our stroma. And we're thinking about being in a thylakoid, and this is the membrane of that thylakoid, and this is the fluid inside the chloroplast, and then this is inside the thylakoid. So you have this thylakoid space here and the stroma here. So the first thing that's going to happen here is we're going to have water molecules, and we're going to send in a water molecule. And remember, a water molecule is going to consist of 2 hydrogens, and it's also going to consist of an oxygen. So we have our oxygen, we have our 2 hydrogens here. And what the light's going to do is it's going to split this water molecule apart, and what we're going to get is oxygen gas. So we have oxygen, or O2, and we're also going to get hydrogen ions that are going to be pumped over here. So hydrogen ions are going to be pumped over here, and we're also going to get oxygen gas. So what we're going to get is oxygen and then hydrogen ions pumped over here. Now, what we notice here on this side is what we call our ATP synthase. And this is kind of like a turbine that's going to be powered by these hydrogen ions. what we're trying to do is create a gradient to power this turbine here. And the way we're doing that is we're getting hydrogen ions from the stroma and we're pumping them into the thylakoid space. And we're also going to get electrons from splitting this water. So when we add light and when we split this water molecule apart, we're going to get these electrons. And these electrons here, we'll say E minus, are in an excited state. So as they move down through this complex here, through this cytochrome, and they go to photosystem 1, what they're going to be doing is allowing for the pumping of hydrogen ions into this space. So there are some hydrogen ions here. Put maybe 2, let's put 3. And what we're trying to do is create a gradient to get the hydrogen ions to move through this ATP synthase turbine. And the whole purpose of this turbine is for us to go through and produce ATP. So this turbine is going to generate ATP, which is going to power the Calvin cycle. So what these electrons are going to do is they're going to move from photosystem 2 down to photosystem 1, and they're going to lose energy, but in the process, they're taking these hydrogens and they're pumping them over to this side to create a concentration gradient. Now, once they've lost enough energy, they're going to end up here at photosystem 1. And at the end of photosystem 1, what we're going to get here is the production of NADPH. So NADPH is formed via NADP+. And the way we get this NADPH is we take a proton and we stick it on the end, and we take these electrons, once they've been excited, again at photosystem 1 by the light, and we stick 2 electrons here, and then we add a hydrogen, and what we get is this NADPH. And then we ship this NADPH over to the Calvin cycle. Because remember, this is going to be powering the Calvin cycle. Now, once we have our NADPH formed and our electrons have moved down and they've gone from higher energy to lower energy, been re-excited, and then incorporated into our NADPH, what we have is a concentration gradient. So these hydrogen ions here, there's more of them over on this side in the thylakoid space than there is in the stroma. So what they're going to do is they're going to go move through this ATP synthase. And there's a special hole in this ATP synthase, and as they move through here, they're going to go through and generate energy to spin this turbine. And what we're going to get is the production of ATP from ADP. So you have ADP, and we're going to generate ATP from this concentration gradient of hydrogen ions. So by going through and using the light energy, splitting apart the water molecules, we get oxygen as a byproduct. We create a concentration gradient with these hydrogen ions, and then what we get is the production of NADPH and ATP by powering this turbine here, and then going through and providing NADPH. All of this goes over to the Calvin cycle. So we're sending this all over to the Calvin cycle. And in the next video, we'll go through and look at the Calvin cycle in more detail. But remember, light-dependent reactions is creating chemical energy from light energy to power that Calvin cycle. So that was a lot of information, but the things we should have gotten out of this is light-dependent reactions, what the electron transport chain is and how it functions, then also going through NADPH and NADP+, understanding how that electron carrier provides energy in the electron transport chain. So this is going to be the end of the video. If you need help, we will be going over direct instruction in class to cover this. So please make sure that you see me either during Lunch and Learn, or make sure that we're paying attention in class as we review this concept. This is going to be the end of the video, but I will see you guys in class tomorrow.